Welcome to what I think is going to be the final video of our two-dimensional shape and three-dimensional shape unit. And we're using it to cover the surface area of curved surfaces, namely for the purposes of finding the surface areas of cones, cylinders, and spheres. So in order to find these curved surfaces, well, in the case of the sphere, it's all a curved surface, but in order to find the curved surface, you must imagine it flattened out so that its two dimensions can be measured and multiplied to get the area. Now, for a cylinder, it's pretty obvious. If you take a rectangular sheet of paper and you curve it, you're going to end up with a cylinder, at least without the two bases. And this is exactly how it looks like when a cylinder's curved space is flattened out. It looks like a rectangle. So, for a cylinder, it'll flatten out to a rectangle. For a cone, you can imagine it flattened out to a triangle. It won't actually flatten out to a triangle. If you look at the net of a cone, it doesn't look like a triangle. But you can imagine it flattening out to a triangle for the purposes of remembering the formula. Same goes for spheres. You're not going to get a giant circle if you flatten out a sphere, but you can imagine it looking like a giant circle if it's flattened out, because that will help greatly with memorizing the formula. So we'll start with the cylinder. So with the cylinder, we of course need our two circular bases, which are each pi r squared. And then we also need the curved rectangular area. Now, if we unfurl the rectangle, we can imagine, of course, that the height of this rectangle is the z dimension. It is the height of the cylinder. It is the distance between the two circular bases. But then what is the width of this rectangle? Well, actually, if you remember, when we curl it up, presuming no overlap, we actually find that the length or the width of this rectangle becomes the circumference of our circular base. And so we end up having a rectangle that is actually the circumference times the z dimension. So if we can get the circumference, then we can get the area of this rectangle. And of course, if we can get the circumference, we can also get the area of this circle. Now with a cone, it's a little bit more complex. You have two surfaces total. You've got the circular base, and then you can imagine a triangular curved surface. This triangular curved surface is going to have dimensions of the circumference and the slant height. Now remember, the slant height is not the same thing as the true height of the cone. We discussed this in our last video on surface area when we were talking about pyramids, that the slant height is distinct from the true height. The slant height of our cone is not the height from the bottom to the top, but rather the length of the cone from the edge of the base to the tip at the other end. So if we can find, or if we're given the slant height and the circumference, then all we need to do is do CS divided by 2, and we're going to have an area of our curved surface. You can also shorten this to r times s times pi, the radius times the slant height times pi. If you're given the radius, then this can be a much quicker version than this one, where you have to find the circumference and then divide by 2 after the fact. Finally, we have the sphere. Now, the sphere can be imagined in two ways, one regarding the radius and one derived from the diameter. But both of them involve circles. The formula for the surface area of a sphere can be interpreted as 4 pi r squared, which could be thought of as 4 circles for circle areas. It could also, if we're going from the diameter, be even simpler, just d squared times pi, which if you imagine a circle with derived from d squared, then you will have that one giant circle, which is equal to the surface area of the sphere. So let's put some of these into practice. A soup can is 5 inches tall and 3 inches wide. How many square inches of aluminum sheet are required to complete the can? In other words, what's the surface area of the can? So go ahead and try this one. Pause the video if you need time. I'm going to be releasing hints one at a time until we get to the final solution. So first things first, the 5 inches that's being mentioned is our z dimension, and the 3 inches that's being mentioned is the diameter of our circular base. Believe it or not, that's all we need in order to get the entire surface area of the can, since we can get both the circumference and the area of the circle from that single measurement. So, if we are relying on the diameter, then we remember that the area of the circle is the diameter squared times pi over 4. Or, of course, you could convert the diameter to the radius and just do the radius squared times pi. Either way, you should end up with circles that each measure 2.25 pi square inches. Together, the two bases equal 4.5 pi square inches. Now notice I'm leaving it in terms of pi right now. I'm not going to bother approximating until the very end. Our circumference is, of course, d times pi. So 3 times pi times the z dimension, which is 5, will yield us a rectangle that is 15 pi square inches. Finally, we add them both together. Our 4.5 pi plus our 15 pi yields us a total of 19.5 pi, which I'll finally approximate at the end to be about 61.23 square inches of aluminum sheet. Next problem, let's get into cones. Each party hat has a slant height of 8 inches. If the party hat measures 6 inches in diameter, what is the surface area of the hat, presuming there is no overlap? So the first thing to really understand is that the party hat is not a complete cone. It's only the curved surface. The bottom is empty. Therefore, we don't need to bother getting the base area because there is no base. Instead, we're just going to focus our efforts on finding the area of this triangle, which is the slant height times the circumference divided by 2. Hello. There we go. So we know that our slant height is 8 inches and our circumference is 6 pi inches because it's diameter times pi. And so pop those into our formula and we end up with 24 pi square inches, which is about 75.36 square inches of whatever party hats are made of, cardboard. Finally, a sphere. Each beach ball requires about 2,826 square inches of plastic. Presuming there's no overlap, and we're going to presume we use 3.14 as an approximation for pi, how far is it from one end of the inflated beach ball to the opposite end? So we know that we're using our surface area of a sphere formula, and I'm going to choose to use the one derived from the diameter because our answer in the end is going to be a diameter. We know this because we're looking for the distance from one end to the opposite end. That's diameter through the ball. That's not radius. So with that being said, we can plug those into our formula. We know that our surface area is 2,826, and we know that pi is being approximated as 3.14. So now we just need to run a little bit of algebra to solve for d. And so we're going to start that by dividing both sides by 3.14, and we find out that d squared is equal to 900, which means that d is equal to 30. So the diameter is 30 inches. And that's all.